So, welcome to this third installment of Lanthanide video series. So, in this lecture, we'll be going through the consequence of lanthanide contraction. In the previous lecture, we understood what is lanthanide contraction. So, lanthanide contraction is the steady decrease in size along the series of elements, lanthanide series from lanthanum to lutetium, right? So, this is due to two things. One, increased nuclear charge plus ineffective or poor shielding of 4f electrons, because of which electrons are pulled closer and therefore the size decreases. So what could be the consequences of lanthanide contraction? First one, there are three, and if you can write these three, I think it should hold you in good stead. First one, some of the plus 3 lanthanide ions are very similar in size to some of the similarly charged ions of the second row transition metals. Uh, for example, if you consider the radius of ytterbium 3 plus, just a moment, not ytterbium. So if you take example of yttrium, not ytterbium, sorry there, it's yttrium. This is about 83 picometers. Now this is very similar to HO3 plus osmium and Dy3 plus. So not hafnium, holmium and dysprosium. Okay, I'm still not getting the names of these. Okay, anyways, so where is yttrium, scandium, titanium, vanadium, yttrium, zirconium, nobelium, right? So this is a 4D metal. Now if you see, this is a second row transition metal, yet this is all three of them, yttrium, holmium and dysprosium, are of almost identical similar size and chemical properties are therefore very similar and therefore difficult to separate them. The second consequence of lanthanide contraction. Okay, so this is the sizes represented in angstroms. So this is the first row transition series, second row transition series. There is the lanthanides here, and there is uh, all the 14 guys here, and continuing with the third row transition series. So scandium, yttrium, titanium, zirconium, hafnium, vanadium, nobelium, what is it? Yeah, tactium, chromium, molybdenum, tungsten, manganese, and so on and so forth. Now, if you take a close look at this, what you will find out is, as you go from top to bottom, like normal size should increases, right? Size increases from top to bottom. Okay, this is what your common sense tells. So from scandium to yttrium, yttrium to lanthanum, there is, of course, there is a marked increase here, 1.44, 1.46 and 1.69. Now what is very abnormal here is, see here, 1.32, 1.45, again it is 1.44. What happened? Magic. See again, 1.34, 1.34, 1.29, 1.30. So the normal size decrease disappears after the lanthanides. So what you find is few pairs of these. For example, zirconium, hafnium, Nb, Ta, molybdenum, tungsten, okay, are almost identical in size. So the size of the third row transition series are very similar to those of the second row of transition elements. Now the this third row transition series, the sizes are very similar to the second row, which means what? Close similarity in size makes chemical separation difficult. Okay, and therefore second and third rows of transition elements resemble each other more closely than the first row and second row. Second row and third row are, there is a close resemblance because their sizes are very similar. And coming to the third consequence of lanthanide contraction. So from left to right as you go, what happens? Lanthanum, cerium, priya, as size decreases, what happens? Attraction between the atoms increases. So which means hardness, melting point, boiling point of elements, all of them increase from C to L. So this is very simple topic, but has come in most of the exam papers, the consequence of lanthanide contraction. So here is the third video on lanthanides. Next we will jump into the separation techniques for lanthanides. So till then, see you all. Bye bye. Take care.